The topic for my research work is nonlinear control system using fractional calculus. So basically the research question that I would be trying to answer in this research work is that if by using fractional order control systems can we outperform the conventional integer order control systems. So what is meant by fractional calculus? So in simple terms it means that it is the generalization of the differentiation and integration terms to an arbitrary order. So as we see that a conventional PID controller has one integral term and one derivative term. So if we raise these integral and derivative terms to an arbitrary order, we come up with a fractional order PID controller. And that is what we would be exploring in this research work. So we would be making a comparative analysis between an integer order PID controller and a fractional order PID controller. So the reason why a fractional order PID controller is expected to outperform the classical integer order PID controller is because of the range of values that it can take, which are represented by the green shaded region in this image. Also, we can see that the various types of integer order controllers are represented by specific points, which mean that they can take only a certain fixed value. Whereas a fractional order PID controller has more degree of freedom, which results in the better performance of the system under consideration. So the system under consideration would first be implemented using a PID controller and then using a fractional order PID controller, and in both the cases the PID control parameters would be optimized using particle swarm optimization and genetic algorithm to give us the best selection of the controller parameters. Well, the reason that I'm working on this research problem is because I have a background in aerospace engineering and where I worked on different types of control systems, and when I came across fractional order control system, it really piqued my interest as to the numerous prospects it has, but they are still not being used in the mainstream technology because of their inherent mathematical complexity. But currently we have many approximation methods and we have strong computing machines which are capable of solving the fractional derivative and integral terms. So the fractional order control systems have been explored in controlling the pitch angle of the wind turbine blades because the airflow is highly nonlinear, and it was found that by using the fractional order control systems we can achieve better performance in the wind turbines. So there are several cost functions that were used in the literature review for optimizing the PID parameters. So some of them were like based on the pole placement based optimization methods, then by reducing the steady state error or the integral errors. So the work methodology for this research work starts by selecting a plant model which we would be considering for our analysis. Then we would select an optimal design criteria based on which we would be evaluating our different controllers. Then we would test the open loop system response, and after that we would introduce a unity feedback system. After that we would use integer order PID controllers and then tune the PID parameters manually. After that we would further improve the PID controller performance by using advanced optimization methods like the genetic algorithm and the particle swarm optimization. And after that we would move on to modeling the fractional order PID controllers, and again we would be using genetic algorithm and particle swarm optimization for optimizing their PID parameters. And at the end we would do a comparative analysis and evaluate which controller performed better. So the plant model that is selected for analysis is the pitch model of a Boeing 747 aircraft, and the flight envelope that we would be considering would be of cruise flight at 40,000 feet at a max speed of 0.9. The nose up and nose down motion of the aircraft around its pitch axis is called as the longitudinal motion of the aircraft. There are two types of longitudinal modes. One is the long period mode, which is caused by the variation of airspeed, pitch angle and altitude, and the other one is the short period mode, which is caused by the changes in angle of attack due to sudden wind gusts or disturbances. For this research work we would be considering the short period mode. The various flight parameters and flight coefficients are substituted in the short periodic motion equation of the aircraft. The pitch motion of the aircraft is controlled by the elevator servos. So for the entire system, we need to take into account the elevator servo also. The next step is to select an optimal design criteria. For our research work, the cost function that we would be considering would be the minimization of the overshoot, rise time, and the settling time. As we can see that the PID parameters have different impact on the response characteristics of a system, so we need to optimally select the PID parameters, and this would first be done by manual tuning, and then it would be selected by using optimization methods. So the next step is to test an open loop system. In an open loop system, there is no system feedback. So as expected, an open loop system is highly unstable. The next step is to introduce a closed loop system with unity feedback. In a closed loop system, we would be having a feedback system which would reduce the error. We can see that the closed loop system is stable, but the performance parameters are not optimal. The next step is to use an integer order PID controller. So a PID controller is introduced in the closed loop system. Initially, the PID parameters are arbitrarily selected and then they are tuned. The PID parameters are initially tuned using the MATLAB's PID tuner toolbox, and we see that we are able to improve the system response in comparison to the closed loop system with unity feedback, but still our performance parameters are not very good. So we can clearly see how our system response has improved by using a PID controller, but still the performance parameters of our system are not very optimal. The next step is to tune the PID parameters by one of the optimization methods. One of the optimization methods used is the particle swarm optimization, which is based on the fact that the collective knowledge of the entire swarm or population can be used to solve a problem more efficiently and more quicker. In this example, we see that we have a swarm of size 4 and we are trying to locate the food based on its scent. So the assumption is that if the scent is powerful, then we are much closer to the food. So we evaluate the fitness function for each individual of the swarm, and we identify the individual which is having the best fitness value. Once the individual with the best fitness value is identified, then all the remaining individuals of that entire swarm are directed towards that individual which has the best fitness value. So this method continues until we reach a point of convergence which represents the best solution. The next optimization method used is the genetic algorithm, which is based on the survival of the fittest principle. So we start by evaluating the fitness value of each individual, and we identify which individuals are having the best fitness value, which are having a moderate fitness value, and which are having a very less fitness value. So in the next iteration, the individuals with the best fitness value would be retained, whereas the individuals which are having a very less fitness value, they would be entirely eliminated, and in place of them we would generate new random individuals. And the individuals that are having a moderate fitness value function would be mutated to get a crossover child which would be having some of the characteristics of the previous iteration. So after using genetic algorithm for tuning the integer order PID parameters, we obtain a fitness value of 2.4652, which represents very good performance. And we can see from the step response plot that the system is having very good performance after the PID parameters are tuned by genetic algorithm. In the next step, we tune the PID parameters using particle swarm optimization, and we obtain a fitness value of 1.05, which is even better performance. And the same we can observe from the step response graph that the system is behaving optimally. The next step is to use a fractional order PID controller where we have 5 parameters to be tuned. And we use the genetic algorithm for the optimization of the PID or the FOPID parameters, and we obtain a fitness function value of 0.7255, which indicates that the FOPID controller is performing much better than its integer order counterpart. We can see from the step response that the system is having very good performance. The next step is to use particles form optimization for tuning the FOPID parameters, and we obtain a fitness value of 0.9570, which is again very less compared to its integer order counterpart. And again, the system shows very good performance. The next step is to do a comparative analysis between all the types of controllers that we have used in this research analysis. And we can see from this graph that the fractional order PID controllers are able to outperform the integer order PID controllers by a substantial margin. So we can see how our fitness value decreases when we started using better and better optimization method, and it's improved even further when we used fractional order PID controllers. This image represents the various fitness values for the various types of controllers that we used, and we can clearly see that the fractional order PID controllers are having the best performance. So we can conclude that the fractional order control systems are able to perform better than the conventional integer order control system based on the analysis and the performance metrics that we have derived in this research work. Thank you.